Good day, everyone. Please allow me to introduce Professor Jose Renau, who is a professor of computer engineering at the University of California, Santa Cruz, where his research areas include computer architecture, infrared thermal measurements and modeling, simulation, FPGA, and ASIC, which gets into the topic of today, and mobile pervasive computing, also in the topic. Professor Renau is also a member of the Cross team at UCSC, which is the Center for the Research in Open Source software that Hugh mentioned. And Cross is one of my own connections at UCSC, and it's a community architect. I'm interested in how professors like Jose and PhD students such as Sage Wheel, the founder of Ceph, who was once who once did his doctoral research as a thriving open source project, and how to do that so that it lives beyond your PhD defense. So Cross, in bridging the gap between student research and open source projects, is able to amplify the translation and impact of university research. And funded by an endowment from Sage, the Cross oversees undergraduate and graduate students who are doing their research directly in open source communities, with mentorship available from not just the academic sphere, but the world of tech companies who are Cross members. So today, Professor Renau is going to talk with us about LifeHD, which is an infrastructure designed for live hardware development that brings small changes in the design and the synthesis and simulation results in just a few seconds. So, and then afterwards, please join us in the roundtable session to continue the discussion. Jose, go ahead.
Thank you for the introduction. Hope that you see the slides well. Today, what I'm going to be talking is the research that I've been doing at UC Santa Cruz for the few years. But before, let me start with a little introduction myself. So as Karsten mentioned, I'm a computer architect. My area of research is traditional computer architecture. So what does it mean? This thing is that I care a lot about high-end CPUs, like the mobile CPUs they might have on the servers, or the CPUs they might have on the phones. And I have done extensive consulting on the Valley with several companies building high-end CPUs. Now, this gives me the expertise, connection with the real industry and see what are the problems. So this is the work I'm being talking is not, it's something that's been done by a large team. So the picture at the bottom is my PhD students a year and a half ago. Now with the COVID, we cannot take pictures. And there are several active masters and PhD students working on this project, also undergrad students. Now, a little background. What if houses were built like chips? And I'm gonna show you what's the problem. So imagine that you have a house and you want to change the door size. So if you were building a house, well, you will increase the size of the door and make it. If you were fabricating chips, what will you do is demolish the building and start again, just because you did a little change. When you fabricate the EDA flow on industry, whenever you do a little change, you always do a make clean. There is no incremental compilation. So everything is redone from scratch. Clearly, it's a waste. Now, in the FPGA domain, there is a little bit of incremental compilation. By incremental, it means that you do a small change, then you can see the results without having to redo everything. And these are two of the commercial flows. Flow 1 is one of the Altera oscillings, and Flow 2 is Altera oscillings. And usually when you do the FPGA flow, you go three main steps. You do synthesis, that's the S, you do placement, and you do routing. And sometimes it takes more time, sometimes it takes less time, but that's the idea. So what are we showing here in this plot? So it will give you the problem. So for each one of the three, the black dot is the time that it took to compile full. I did a make clean, make. That's the time for synthesis, time for placement, time for routing. And then in the other flow, it was slightly different the times, but that's the time. What are all those options that we have, like a bar? I changed a comment. Clearly, I didn't change the design. I just changed a comment, and I tell the tool recompile with incremental enable. So what happens? In this flow, the synthesis took the same time. This is just variations, noise on the random machine. The placement got much faster, but in this other flow, it didn't. Now the synthesis got half. So, and in routing, neither of them improve. So what is this thing showing? That the best of the best that you can commercially buy now, there is no incremental as effective as it should be, because here I just change a comment. It should be very efficient. So in practice, there is around 20% time reduction for most designs when you start to be big. Now, how is the current chip fabrication? Because of those very slow times. So typically you have an RTL designer that it works making the programming a language like Verilog to specify the design. And from time to time, it will commit to a repository. And then a few hours or days later, a backend engineer will load this design because it has make clean. It will synthesize the design. It's very common to take 6 to 24 hours to do the backend because it starts from scratch. And then it passes back the feedback because it takes many days to get this feedback. Many companies, in a company I was, they were giving the feedback on Fridays. In some other companies, they give you the feedback the next day. But because there are many changes that you have done, you have a combination of changes that you have done, and then you see the feedback, and you have to try to figure out what's going on. It's a very difficult interaction, very long loop. And what we're saying is that it's a little bit worse. So why do I have a Dory here? Because in a way, we are all Dories. So what do I mean by this? Is that to solve problems, we only can use the short-term memory. We cannot use what sometimes is called mnemonic memory. And you hold concepts there for 2 seconds to 30 seconds, depending. You're superhuman, 30 seconds. But most of the people, a few seconds. Which means that if you want to have quick iterations over a problem and an idea, you want to have the feedback in a few seconds. If you have more than a few seconds, your productivity goes down. This is why there are so many studies showing that if you are working and you get a phone call, even if the phone call is, let's say, 1 minute, you lose like many minutes, like 20 minutes in many studies, because it takes you time to rebuild your memory. It takes you time to rebuild your short-term memory, and you need to rebuild your short-term memory to solve the problem. So we want the response time in a few seconds. The tools are given response time much longer. So how should it be? So we should have an incremental flow. So I sort of make clean the enemy of my flow. It should support make clean because sometimes you want to do it, but you should never work assuming that you have to do a make clean. It should be very fast feedback. Now, what is the time frame? Obviously, it will be very nice to have millisecond response, but that's not reasonable. So the reasonable response time is in the order of a few seconds. So the order to achieve this is by doing incremental. If it's not that we want to get a worse quality result, it's the same quality of result, a QOR that we use in EDA, but it's an incremental change. Sometimes it's going to take time. Sometimes maybe you change the bit width of a processor, it has a ripple effect, and it takes a long time. Fine, but it should be infrequent, that case. Now, the third thing should be is that the hardware description language that we are using in the EDA is Verilog. It's the de facto standard. And it's a language from 1984. So it's showing the age. So in 1984, it was very different. There have been improvements and they have the system Verilog, but that's more like a language by committee, which they have been adding a lot of features that nobody likes all those features. Let's put it this way. And there is a lot of research on the academic side that we see Verilog as the JavaScript, as an assembly, but you have to have a higher abstraction. And there is a lot of competing platforms trying to build it. Now, the problem is that, and ideas, but the problem is that if you want to develop a new language and you want to make it incremental and very fast feedback, it's a lot of effort. So what we are trying to build is a platform that allows you to design new languages or use Verilog if you want, and to have a very fast feedback, very scalable. So why the new language? And it gives a little of idea why we started this project. So we started a new language that we call Pyro in our flow in 2006. So this is a long time ago. And the reason is because in 2006, we started to build an out-of-order processor because that's my research, as I'm a computer architect. But we found that the tools were the problem. It was not so much the how do we specify the problem, it's that the tools were very slow. It was very difficult to guess what's the frequency, and you had to do iterations and trash the code and redo it again. And there were a lot of different problems. So in 2 years later, we say, okay, this is the wrong area of research. We shouldn't be doing this core. We should be improving these tools. And in the way that we started, because we saw the problem on the language, we started with doing a new language that it was Pyro. And Pyro is not Python rope. Pyro is a stone that resembles Ruby. And the reason, because in my research group, we were using Ruby for prototyping. And we were copying a little bit the syntax from Ruby. So, but by 2016, after the PhD has finished of that student, we realized that the language is only part of the solution. And then when we are starting this new project I'm talking about, the LifeHDR. So the Pyro is solved some of the issues, but you still were having all those similar problems. The response time was very slow. You were having a disconnection between logic and the synthesis. So the flow is more important than the language, or at least as important. Obviously, you have to program in assembly. It's not great, but imagine that every time that you compile, it takes you hours. So that's, maybe you prefer to program in assembly more than in Java. You have to do 8 hours for every compilation time. And so we build the language because we think that's important. It's not that we think language is not important, but the flow is what we are focusing here. So what is this new flow that we've been working is what we call the LifeHDR, or live hardware development. And the idea is it's similar to a compiler infrastructure, but for hardware. That it has the goal of being incremental and scalable. So we want to go fast, and we want to be scalable for large designs. And you build your compiler passes, like that you might have on your flow. And then you can interface with other tools, like, for example, interface with Josys to read Verilog, or Josys to output Verilog. That was one of our first passes. But as we keep progressing, we start to build our own passes without interfacing with Josys. And many passes can be added, typical compiler passes like dead code elimination, or finding logical equivalence between blocks. You can build your own passes. And we can start to interface different languages. So we started with Verilog, but clearly we're working on Pyro, as mentioned before. But there are some other languages that are very popular, like Virtual, that is the low-level representation from Chisel, is a friendly competition from Berkeley. So it's like have good relationship with them. And we're trying to support Virtual because it's a language that is getting a lot of traction due to the RISC-V community. And in the outputs, you want to output the languages again, and sometimes C++ for simulation. Obviously, we focus on the C++, on the Pyro. But one thing that we've been doing on the flow is like all those languages, when you translate to a language to the flow, they share a lot of infrastructure and a lot of code. And this is something that we've been trying to clean up. That is what we call the language neutral AST. So that if someone ports a new language in the future, it's very simple to add it, and then it can leverage the full infrastructure, the incremental features, the fast scalable design, and a much easier way to build a full language. So that's the LNAS part of the project. One thing that is different is that in Pyro, we can interact with any other language. What we think is more easily, so it's like a little Borg. We're trying to absorb the other ones, but it's a language. If you want to build your own language alternative to this, you can do it. So where is the repository? So it's on GitHub. We have been working on the open from the beginning, which means that from the beginning we were working, the code was not ready because we were working. So it's an evolving project there. So there are two main components. There is the LGraph, which is a graph SSA netlist representations. And there are many passes for hierarchical traversal, topological sort, many things that usually you need in synthesis. And the LNAS, it's what I mentioned before, is the language neutral AST to make easy to input and output new languages to the tool. So the incremental flow, let me quickly go over a couple of things that we are trying to get. We want to get the flow to be very incremental. Now, what we have been doing before we started to implement, we were doing projects, papers, in which we prototype things in Ruby. and then we publish a paper like this year on ISPAS. What we are doing now is bringing all those papers to the simulation. So the thing I'm going to be talking now is things that they are still not on LifeHD, but we are actively working to bring towards it, because we have published papers before on this, but we built with a different prototyping language. So what is one of them? Incremental simulation. That's something that current tools don't have, is that you can run a simulation, do a code change, and then reload from the checkpoint and re-execute. So the simulations are slow when you model hardware. So you can run maybe a few million instructions, do a code change, and do a hot reload. So you can do hot reload with hardware. That's something that you can do in some languages, like JavaScript allows you to do this. C++ is much harder. But we are doing hot reload with hardware description languages. Now, we want to go very fast in incremental compilation. So Verilator is a competing system that's for an SoC. And we see that we are very fast compiling. Again, our target was the 2 seconds goal, and we were able to achieve that target. The tool in the simulation, we are trying to go faster, or at least as fast as the competition. That is Verilator. Is the fastest Verilog simulator you can have around there, at least for not super large designs. And we found that we were even a little bit better, not because we're targeting to be better, but because we reduced the cache footprint in order to be incremental. So it was having a little better performance, but if you have a small design, Verilator was a little bit faster. Now, one thing is the simulation that we are trying to add now. The other one is the incremental synthesis. That's something that I showed at the beginning, that the commercial flows don't do much incremental synthesis. That's a paper that we did. So these are our parts that we did on the paper. And this is the parts from Vivado. We were using the TCOL interface with Vivado. Now what we are doing is porting the same concepts, but working with the open source synthesis. So there's a group of open source synthesis, and they are better performance, and we're interfacing with them, trying to get better results. We think we can get better than Vivado, even without incremental. Once we add incremental, our goal is to go to the sub 10 seconds. Now, we have several publications showing the scalability, and this is already on the LifeHD. This is a flow that is with another open source flow that maybe is the most popular now, that is called Joses, translating from Verilog, and then that was with Pyro. This is what it was 1 year ago. Maybe I have time to do a little demo. You will see that we are getting much faster than this. This is the flow that we are having now. When we go through the LNAS representation instead of going through the internal representation tree. Now, as I mentioned before, we're interfacing with synthesis tools. So this is there are two main open source synthesis tools. There's ABC and MockTurtle. So we are benchmarking both. We are tracking the quality of results of both, but we are focusing mostly on MockTurtle because it scales better and we can get better results. So how can you help LifeHD? And this is just to closing up, and then we can go over potential questions. So you can help with documentation. As usually, most open source projects documentation is not great, but we have a couple of, we have a website with Slate documentation for the LNAS. We have some documents in the GitHub repo itself. But for example, one thing that we have pending is to set up a Doxygen C++ documentation to start to document the API. It's always good to create some small, interesting test cases. Small because it's easier to debug. If it's something big, it's very difficult to debug. And creating tests to increase coverage. So we enable test coverage in our flow, and we're in the 70%. Obviously, we have to go up, but it's difficult to create tests that hit the missing coverage. We are working to interface with NextPNR, so that's an example project someone can go. And there are several projects, smaller or larger, on this link that I try to keep up to date. But if you are interested in helping, contact me. I might be able to find some tasks for you. So what is the summary? So we are trying to do a more productive flow. We want to be incremental from synthesis and simulation with hot reload. And we want to be scalable in synthesis and simulation. and to interface with several different languages. So that's the main thing that I wanted to go. One thing that I have is I can do a demo. Let me see how is the sharing the screen. So here what I have is two machines. So this is one machine that it's, you look why it's happening here is because this is my phone. So this is the machine that I'm running now, is my phone. I'm running the synthesis on the phone. So this thing is so relatively fast that I can even use the phone. So how does it work, the flow? So if there is a console, and for example, if I want to test a language, Pyro test, compiler, let's do logic.prp. So this is just an example of the language in which you specify the bit width, and there are some very simple operations. So in the flow, you specify what's the file that you're going to compile, Pyro test compiler, logic.prp, and then once you have it, this creates the LNAS representation that I mentioned before, but obviously this is useless. What you want to do is to convert to internal representation, LNAS to LG, and then you might want to do compiler optimization passes, like these two passes. Notice that I just hit enter and it finished. So it's not that it was a mistake, it's very fast. So how fast? So we have some synthetic tests, but they are very long. Like for example, I don't know if I have word count here, but if I do, this is 10,000 lines of code of a test. It was doing additions and it's doing several operations. So if I run this thing, so what is the flow? I'm gonna run 10,000 lines of Pyro and then compile and optimize to generate the code, and it finishes in 0.7 seconds. And that's on my phone. Now, if I do an equivalent 10,000 lines of phone in Verilog, so I have the equivalent Verilog. Instead of doing 50,000, I do 10,000. I run it. It loads the design. It's optimized. This is Josys, which is extremely fast. This is much faster than most commercial flows. That's the open source alternative. Claire Wolf works with this flow, and we're interactive with them. We even went to a combined proposal in the past. And this is the work that we are doing. So that's okay. So that's the problems of having kids at home when you are working. So notice that it finished in 30 seconds. And we are finished in 20 seconds. Now, there is the options of different benchmarks, like an XOR chain. It's able to optimize faster in Josys. Finishing 1 point. For some reason, it gets more slower with it, but it has more problems with the XORs. In our case, we are very scalable in both ways. So this is the idea of what we can achieve with this flow. That is it's a very fast flow, very incremental, but it's still early on the design. In the sense that if you were still working on them, there are many of those paper features that we're implementing, and we still don't have them. But it's a perfect time for people to try to contribute or try to provide input and feedback. Now, there are several parts of the flow that they might be more mature or less. If you want to help in If you want to use the flow, there are several parts that are mature enough to use. If you were trying to port a new language, I would say that you should wait a little bit because we are porting several languages. Like, for example, even on the phone, it works. So here is reading Pyro, but instead of Pyro, I can do Fertile. What it's going to be doing is the same benchmark, 50,000 XORs with Fertile, this chisel, and it's able to run it in 2.6 seconds. Now, as a reference, if I use the Fertile flow from Berkeley, it takes around 10 times more. So we're talking about being very fast flow, but still not fully stable in the Fertile side. So those are the main things that I wanted to go over.
Yeah, did you, and we were talking earlier about the way that a new language can be a unifier for a developer community, and I was curious about what part do you think that Pyro can play in bringing people along to using this infrastructure?
So on the Pyro, the language, so it's what I mentioned before. So we all sort of agree that Verilog is the assembly of the hardware description. But like an assembly, no, you should not program with it so much unless you really care about it and you got used to it. But a lot of part of the community, like in Berkeley with Fertile or in Cornell with Pymetal, we think that we don't want to lose performance. So it's not that we want to lose performance, but we can do a better design. Like, for example, in the Pyro, this is the syntax that we have. Now, what is the thing that we can do that we think is better than the other alternative flows? Is that we built it on the language, something that is called fluid pipelines, that it allows faster and more freedom on the transformations on the synthesis. So we're embedding things on the language that it gives more freedom to the tool. That if I specify those things on Verilog, then I don't have that freedom. Then the other things that we're doing is that we have a global type inference, which most of the newer language alternative to Verilog, they have a local type inference, which we think that it really helps on the hardware design. And we do prototype inheritance like JavaScript, because in hardware, you don't have so many objects because you are not going to be populating objects like in normal software. But doing the prototype allows you to customize to have a list of methods for just the thing that you do in your module. So we think that things like that, it might make the language a little bit cleaner and better. But the question is on the air. So really, there are many languages there. We are trying different approaches, and we'll see how it works. What I think in all the cases, they agree is that the flows have to be faster. This make clean is not an okay thing. So the language, I see them competing is unclear. The response time, for me, is very clear that you cannot afford those horrible response times that we have now.
Yeah, and I was glad to see that you had some materials in there for the contribution pathway. And I know that's always a tough one. You and I were talking the other day about how how the value of getting early attention and how all that can kind of go as well. And yeah, I thought maybe we might, in terms of the you were talking, some of the discussions were going on in the stage side where folks who hadn't seen your work before were really looking to connect up what what you're doing with the tool chain work that was discussed right before we went on. So we probably didn't get a chance to see any of that, but that's some of the follow-up we went doing. So that seems like that would be kind of a user base, but that's also a user base who's also contributor base. So that kind of interesting little crossover where you get somebody who has a little bit of a contribution audience.
Yeah, the current status, if I go to the contributions, most of those things, it's more like a developer. So there's the co-developers and there's the user. Yeah. So the user, I will not advise to use it now. And mostly it's because there is the flow, it works for many things, but we still have not fixed the error reporting message. So if you don't have any typo, it should be okay most of the time. But you miss a semicolon. If you miss a semicolon, then it's gonna flag an error, maybe failing an assertion. it's going to be very catastrophic failure, because there is a student working now to try to report the error, improve the error reporting system, and try to be better, but still not there. So until we don't have that as a user, it's very painful to use it. You miss a semicolon and a seg fault, that's not the way to go.
Yeah, it's really disappointing. So,
yes. So, yeah, wow. But the developer, you know what's going on. You can contribute in those things.
Yeah, that was the. You mentioned that the student is working on that. How has the interaction been for you in terms of making actually this part of people's actual academic work?
So if I go the list here, so the current students, the first the first 3 students are PhD students, and the other one, the next one is master, and then there are undergrads. So so it really depends on what they are doing. So if they're undergrads, that's the easiest because they help on the infrastructure, they learn how the thing works, and then it helps them prepare to apply for grad school if they want to go to grad school, or for industry because they get experience of the full real flow and everything. If they're masters, usually they pick a section on the project. Like, for example, this student, that is Eric, what he's doing is porting Verilog to our LNAST. And it's a very independent kind of thing, and he can get a master's thesis from it, and then it brings the infrastructure there. Now, the part is a little more challenging for PhD students, because on PhD students, they need to have publications. They need to have the key novelty. And by doing infrastructure, you don't have a key novelty. So then there is the challenge: how much infrastructure do I work? How much paper? Because there is a lot of infrastructure on their thesis, they are having less time to focus on the novelty paper, but there is the impact of the infrastructure. So there is a trade-off there, but I understand that it's important for them to have publications in the top conference. So then we always look for some new idea, like what we mentioned before, the incremental synthesis. How do we do better incremental synthesis, which is a challenging problem? And then we publish those things in DAC, and then we're trying to port those things to the infrastructure. So there is a little pull and push there. But the graduated students, so it's Intel, Apple, a smaller company, LinkedIn. So all of them, it's like they're able to get good jobs because they have a very good experience on the flow and learning flow.
Yeah, and so it sounds like to some degree some modularity of the way the infrastructure of the programming base is, it helps at least the undergraduate students be able to come sort of plug in but in particular it sounds like the masters being able to work on a discrete portion of something where the success of their master's program is not necessarily tied to the success of all the other efforts that are happening around them, right? Yeah. Yes.
And in the undergrad, for example, Maximilian, the thing that he was doing during the summer is that we have this LNAS that is a tree-like structure, like an AST. And what he was doing is a pass on the compiler that when you build the tree structure is correct. For example, you can build a tree and you can do an assignment and forget the assignment. Or you can do several mistakes. So it did a compiler pass that if you do a mistake, it tells you this tree is incorrectly built. So you can build passes like that. Another undergrad is doing a floor planning tool. By floor planning, it means how to cluster sections of the design so that then when you pass to the placement, it has different implementation. So how they do that is like we pick a paper, say implement this paper in our flow. And then that's something that and the undergrads can do. So it's to get some existing paper and to implement it on our flow.
I had a question for Jose.
So,
yeah.
Oh, yeah.
So you mentioned earlier that you can find places for Red Hat people or people from other universities even to be working with you. Does that happen very much so far? And are you actively trying to encourage people to join?
So there is, so I'm actively looking for people from outside to try to help, but it's a little bit tricky because, for example, there was a student from Iran that he was trying to help in a part of the flow, but it was a very complicated part of the flow.
Mm-hmm.
And then it was a problem, it couldn't finish it, that part. So there are easier contributions. The ones that I mentioned, I think they are easier because there is the time lag contribution. But if they want to try, I was explaining how to try to do it, but it will be a challenge thing.
Yeah, Verilog is a hard thing to pick up.
Yeah, there are some easier tasks, there are smaller tasks. The easier task, I think it's good. The other one is, what I've been also looking is other PhD students. They are not going to be contributing so much here, but they might want to use the flow for something different in their research. And that, for example, something that I've been talking to some professor in which they need to read some Verilog and they need to do a pass to detect if there is a leak of information. So how do you do that? Is that you annotate the net list on the design, and then you propose some algorithm to annotate the net list, no? By using our flow, they can develop their paper. So it's more a user, but it's a little advanced user. It's a PhD student usually, so who knows that it's going to be some challenges here. Yeah. But is willing to put the time because it's part of the infrastructure. No matter what they pick, there are going to be challenges. So I think that here there will be less challenges in some things for him or her.
Mm-hmm. Mm-hmm.
So and that's the other one that I'm looking more advanced users.
From the engineering point of view, it would be, so what we often do is have engineers who have a certain amount of their time that they dedicate to doing research. So it would be mm-hmm. somebody who was interested in hardware or Verilog or wanted to help with advising a student. Is that the kind of thing a Red Hat?
Yeah, that can be. Yeah, that's one. Then the other one is our flow is very compiler-like.
Mm-hmm.
And there are many things like compiler optimizations that they
totally software. Yeah.
So, like for example, some of the competing flows that is EPFL, but they don't have the incremental. The incremental is the thing that we have difference from everybody else. Mm-hmm. Then Chris Lattner, that is the creator from LLVM, is working on sci-fi and is doing something circuit, which has some similarities to this. So there is a lot of flows that are trying to compete and alternatives how to do those things. And nearly all of them are open source because the industry has been very close. Mm-hmm. And the problem is, like, for example, when we did our work with incremental placement. So we wanted to do incremental, how to place the cells on the chip. The flows don't provide any API or anything, how to change it. So it was very difficult research-wise. How do I try to improve on those tools? So there is no way for you to get the hands on the code and try to say, if I change this thing to do incremental. And if you start from scratch, it's totally different. Your quality of results is maybe 2 times worse. So it's like, will this thing work? Won't I have a good quality placer? I don't know. So research-wise, the fact that they've been so close is a problem.
Yeah.
So that's why there is a lot of push from academia to try to make more open source flow because there is no way to do good research otherwise.
Yeah, so Ahmed Sanallah, who was one of the Red Hat conversation leads for the FPGA, the GPU to FPGA talk, mm-hmm. He says the same thing. He's working with Red Hatters and some university students from University of Massachusetts on trying to support open tools for doing place and route and the whole pathway from design through production, and they run into the same issues.
Yeah, so we are trying to focus on, at the beginning we're trying more ASIC, but really our flow is anything synthesis, anything simulation. Mm-hmm. And because there is a bigger user base, we are focusing at the beginning more on simulation and FPGA synthesis and place and route.
That makes sense.
But we're starting from the synthesis up. But the flow you really can handle ASIC too. But the algorithms for placing ASICs are different and they are not there.
There's a question from Hugh, Karsten. I'm going to stop now. Thank you.
Oh, sure. Yeah, I can pass it on if you can see that, Jose, on the side. Hugh asks that you mentioned Intel. How much support are you getting from them in terms of opening up their tools?
So I met both teams, and Intel and Xilinx, many times. I tend to get a little more support from Xilinx. They're a little bit more open, like they have the rapid write that they open source recently. Intel, I remember, maybe it was 3 or 4 years, time flies. I was trying to tell why not to open source? What is inside the culture and here? And it was like, open source? Why? It was not even they have not even questioned that idea. It have not even come to their minds. Why to open source the FPGA flows? That's like 3 or 4 years ago. Now I'm sure that they have thought about that. At least I brought the topic 3 or 4 years ago. But it gives you an idea that those companies are not really ready for it. Xilinx is the ones that I see that is the most from the big players. And the reason is because they see some potential, but they are very protective from some things internal, like how to do the detailed place and route on some of the things that they will disclose the technology. The ones that are fully open sourcing now is the smaller players. So there are many players in China that are trying to do little FPGAs, and there are some very small players that they cannot afford to have the full flow. So what they are trying to do is try to open source fully, completely. In the case of Xilinx, so there are open sourcing many things, but there are still some things that they want to keep inside because of fear. But those smaller players, they are opening everything. That is slightly different. So I think that there is being pressure, and there is going to be more and more pressure on those platforms.
Yeah, this will be very interesting. I decided I would just join and actually talk. The Amit has been working. He's been working a lot with rapid write, trying to. There's some reverse engineering that has to be done to really make it work. But I think the Lattice folks. We had a Lattice board that we started with, and they were quite open, but the board isn't big enough to work with.
Lattice is the one that I was mentioning, is the smaller players. Those they have fully open source.
Yeah.
And they passed the spec to the Xilinx team, and even recently there was a tweet that would say, "Oh, we might close something," and there was a lot of tweets around it, and they said, "No, this is a confusion. For sure, we're going to support open source flows." There was a misunderstanding. So they're clearly trying to push the open source side, those smaller players. And Lattice maybe is one of the best examples.
Yeah. Well, it's going to be a really interesting space to watch. I'm absolutely convinced that there's going to be much more pressure to enable real software developers to innovate in this space. Because I don't think we can continue developing hardware the way we have historically developed it. It's just too slow.
Yes, so much of the things that are trying to improve productivity, and that's in our case is by the incremental. But for example, I think it was released like a couple of weeks ago. Google just released a new hardware description language, and the thing is to improve productivity. It's XLS. And I've been talking with them in the past because the backend has quite a few similarities to what we're doing. And they started the project earlier, so we couldn't interface. But we keep talking. I think most of the teams we have friendly competition, in the sense that there are like many teams. We know what they are doing. We keep talking. We're trying to see how we can interact. But it's a difficult thing to coordinate the teams, and many times they don't integrate because it's difficult to integrate. Integration is always challenging. But there's the Fertile team, there is this team in Google, there's the Time Sci-Fi that is starting with Circuit, which is similar to the to the team from EPFL that they have combined now. And those are the ones who have the main flow. But then there are many little parts here and there. And the main, really in open source most used now is JOSIS. It's from Claire Wolf. It's in Austria, University of Austria, but it's the symbiote. JOSIS is the de facto backend that everybody uses now.
We used UCSC recently. There's just quite a few bugs in there. I think in some parts it confuses the Xilinx tool with the Lattice one. So there are limitations with symbiotic with UCSC. It is good, but there are limitations. So it is still a bit off from where we see the proprietary vendors having their synthesis tools stand.
Yeah, the tools that are still not in competing quality or results with the commercial tools. In the Lattice, because it's a small FPGA, maybe it's there. Because it's a smaller space, a smaller FPGA that can be competing. They're still not competing on the FPGA synthesis, or much less on the ASIC. On the ASIC, they're still farther apart. But on the simulation side, that's not so clear. And I think they're eating it up. Like, for example, Verilator, even there was a talk from Tesla that they were using Verilator for the simulator in a hot chip stock because it was much faster than the commercial flows. So they were doing those things. So there is, it's not there, but it's getting closer. So that's in the way I see it. And in some places like simulation, I think it's really a viable alternative in many things, unless you do UVM or things like that. But in the synthesis, it's starting to get closer. And the smaller FPGAs, I think it's very close. In the bigger FPGAs, there is a challenge still.
The major limitations, so one of the recent projects we were trying to build an open source DDR3 controller. And one of the major limitations we had with the symbiotic tool was with the PLLs and getting the FPGA to run at 200 megahertz versus 100 megahertz, which it was stable at. This was an edge class RT-A7 board. So there is some things that we just found that the proprietary tools tend to give to do the better job, not just in terms of performance, but also in terms of functionality. And that for us is the biggest concern, because when you're developing hardware and something doesn't work, doesn't work right. If the tool is the one that's causing the problem, that just makes it all that much more difficult to debug. Because then you're looking through your code, you're thinking, well, I must have done something wrong. And then you're scanning through all those lines and lines and lines of Verilog code, and then at the end you realize, wait, it wasn't me, it was the tool. And so that kind of thing really sort of pinches. So there are some functional limitations. So for example, when we do something now, we first test it with Xilinx tools to make sure that the code is correct, and then we try to port that over to UCSC and then XPNR. You try to use the open source flow for that. So it does work well for some cases. There are some applications that actually there's some really good demos out of it. But one of my biggest concerns is the functional problems that exist with this tool. And because those are things that are really hard to identify, and you have to be absolutely sure about your code.
But it's correctness or it's timing things? Because correctness should be fairly reasonable, but functional correctness?
Yeah, functional.
Because they have a LAC, logical equivalent check, and they tend not to fail on that side.
It's interesting, because let me give you an example. I was trying to put together a demo for using rapid write for place and route. And I had a simple adder example. It's like A plus B is equal to C. And the adder, when I tried to implement that using behavioral logic, it did something very weird. It would try to synthesize in some carry logic. That didn't work. And then when I replaced that behavioral syntax with actual bitwise logic operations for each bit of the adder, that worked perfectly well. So
yeah, the thing like rapid write, I like them. I like that team. We were trying to interface, and because it's Java, we're having a very hard time. And in the place and route, it was it has some issues. So there is some uses for rapid write. I don't think it's a substitute for doing place and route.
Have you tried
I think it's
using,
more for moving blocks and create macros and things like that.
have you tried using Jupyter Notebook for they have a Jython, I don't know what it's called. So basically, they do support Python now. So you can boot up a Jupyter Notebook and use Python to access the APIs.
Yeah, in our case, because we do everything in C++ 17, and we have a Bazel build system. So then really to integrate a Java system there, we're having to use Graal, and it was a pain. It was a real pain to interface with Java with a C++ flow. And then we're having some other problems on the synthesis that you were mentioning, that is not able to place everything, and then you have to crawl Vivado with the DCPs that they generate. So then it's like, oh, what's the point? We end up calling Vivado most of the time. So then we decide, okay, fine, let's try NextPNR. So now we're trying to interface with NextPNR. Yeah, so there are some things that you try things and waste one master student trying, and I have a 50% failure rate on projects. And by failure rate, it means I learn a lot. I learn what not to do, but it's something not to do. With PhDs, I try to have not such a high failure rate.
Yeah, it uses up more years.
Yes, and it's way more painful. No, it cannot be. But master is a quarter or two, and you learn a lot. It's only that what you develop is not used. Mm-hmm. That's the difference. And I think that's okay. Yeah, 50% by failure, it means that the project that they did, it didn't get integrated into the flow. They still finished the master thesis. But what it means is that the software developed, it was not performing what we thought it would do, so we don't integrate. That's what I mean by 50% failure. It's not that 50% of the masters never finish masters. Yeah, still did the thesis. Right. Otherwise, my department chair will not be very happy.
Well, we obviously have a lot more discussion that we need to have over the long term. Normal times, I would suggest a trip to Santa Cruz, but we'll have to do it virtually for the moment anyway.
Yeah, if there's people interested in the flow, like as a user or developer, let me know. As I mentioned before, the flow is still early. So there are some things that are okay to use, some things not so okay. As I was mentioning before, like for example, now we can parse things like boom from out of order processor from Berkeley in Verilog. But if you move a semicolon and you remove it, it's gonna give you very bad errors. So as a user, that's not the way that you want to have the flow. So we're still improving this. Now, if you want to build your own compiler flow and try to annotate some netlist to do TMR, yes, to do something simple that you can do easily with the flow, that's something that the flow can allow you to do.
Well, hopefully we'll be able to have you all out here in Santa Cruz, maybe sometime next year or the one after would be really nice to show everyone around the things. So a lot of good things happening.